Hello, everyone. So it's a real pleasure to be here and to have the opportunity to present to you my work. It will also be a training for me since I will defend my thesis in now 1 month. So I will perhaps make a long introduction that some of you know a lot about it, but it's still good to have some reminding about the field. So we are talking about radial velocity and the kind of planet that we can detect by radial velocity. And if you look at the planet detected by only radial velocity method, so without the help of transit, you can see that we have some difficulty to go lower to 1 meter per second in amplitude. And it's really a strong difficulty in particular because if you look what is the Hertz-like planetary signal on the sun, it's 10 centimeter per second. And if I plot on that graphic the isomass of a 1 Hertz mass planet or even an 8 Hertz mass planet, you can basically see that above 100 days, we don't find planets even at 10 Hertz mass. So actually, if you look now the archive, there is signal that are falling in that region. For instance, you have this signal, which is a 300-day planet, 60 centimeter amplitude. So there is such signal. So the question is, okay, did I just found a super Hertz in the habitable zone? And in fact, no, it's not the case. I will try to convince you because now we are able to correct for that. Actually, this is the signal was induced by an instrumental systematics. And in fact, this systematics was the aging of the thorium-argon lamp on ARPS. And what is super nice is that I will try to convince you, at least, that with the line-by-line RVs, we are able today to calibrate the calibrator, which is the thorium-argon lamp. So it's just a kind of teasing. It will come at the end of the presentation, but you will see that I think it's super nice results. Just as a reminder, so about the introduction, so what is a radial velocity point? So a radial velocity, of course, you observe the sun, so it's an indirect method of detection. Because the star has some complexity, there is some movement at the surface of the star. Each star has some movement, has some velocity field, you can expect a radial velocity counterpart. So we all know that we have a lot of different components that are contaminating our radial velocity measurements. Stellar pulsation, granulation, active regions as well, that are evolving on longer time scale about magnetic cycle. And you have even other effects that I don't mention because according to me, they don't have been proven to contaminate the radial velocity so far, but there is other effect that theorists predict should contaminate our radial velocity. If we focus on the active region, which is then the main problem that we have, one of the effects is the inhibition of the convective blue shift. So what is happening is that if you look the bisector of your line, which is, I remind, a tracer of the velocity field in your stellar atmosphere, if you look the quiet sun, for instance, you see that the bisector has a C shape, which is a tracer of the granulation field inside the atmosphere. And you can see that the zero radial velocity is the vertical dashed line. And you see that if you look deeper into the star, so if you are closer to the line continuum, the velocity field is higher, basically. So this is true for a single line, but it is also true actually for all the line of your spectrum. So it has been shown by Reimers et al. You can clearly see the convective flow in the atmosphere of the star that are changing with the depths. Now, this is only the convective flow. Actually, if those flows were constant with time, we don't care so much about them. The problem is that then you have an active region. You have the active region has some magnetic field, and it will remove, in fact, the convective flow. And this is what is shown on the left. You see that inside an active region, you have the red bisector. And if you look what is the inhibition of the convective blue shift, typically in the shallow region, you have a factor 3 between the deep in your lines and shallow lines, in fact. And try to keep in mind that factor 3 because it will come later. So this is the inhibition convective blue shift framework, if we want. Now we have another effect, which is also the fact that the star is rotating on itself. So it introduced another effect that we call the flux effect that you see on the top, which is when you have, for instance, the sunspot, there is a contrast, and so you break the balance between each receding side of the star. And of course, both effects are not expected to contaminate the same star. So on fast rotating star, you are dominated by the flux effects, whereas if you are on the inhibition of the convective blue shift, this is more for sun-like star or slow rotating star. It's not the only problem that you have, because when you observe the star, the photon is going through the Earth's atmosphere, and the fact that we observe from the Earth has some implication as well. Typically, you have some, for instance, seasonal gap, and the seasonal gap is a huge problem when you try to find the period basically of in the habitable zone. But you also have other effects. For instance, if you observe at higher mass or lower mass, you change the flux balance of your spectrum. This is what you saw on the left. The blue, it's a spectrum at lower mass, whereas the red, it's at higher mass, so you lose the blue part of the spectrum. You have also the complication like telluric lines. So this is the line that are inside the Earth atmosphere. And because the Earth is rotating around the sun, depending where you look on the sky, those telluric lines are drifting on your stellar spectrum. So they are drifting, and they are also changing in depth, simply because the water content change from night to night because of cloud or so on. The last effect, it's about the instrumental. So we had a really nice talk last month about it, and you have also a lot of other issues. I think today we have really precise instrument, but according to me, I think on the long time scale, the instrumental schematic are still the main problem. If we are talking about long-term period, we are still dominated by the instrument and not for the star, so according to me. And so this is somewhat the full framework of the radial velocity point. You have all these components, and you have to try to correct for them. So this is how now you extract a radial velocity from that. If you look in general, you always have the same schema or the same step to perform. When you have two spectra, you have to fit the continuum in some way of your two spectra, and then you have to measure a relative Doppler shift between the two of them, or between the reference spectra, in fact. Now you have different way to compute that radial velocity shift. I go very fast because you know all of that better than me. The first method is the CCF. So what you do is that you cross-correlate your spectrum with a mask template at the location of your stellar lines. So this is what is shown in that animation. You have the mask, which are the vertical blue lines, and you see the effect of the cross-correlation on the right, basically. And it's similar, in fact, to simply make a weighted average of all the spectral line in your spectrum. And CCF, it's a very convenient when you have additive term, like for instance, when you have moonlight contamination. However, it's really inconvenient when you have non-linear term, which is the case when you have transmission spectra. So if you have, for instance, tellurics, the CCF, it's really becoming a pain. Then you have another method, which is forward modeling, or it's entering into forward modeling classes like least square deconvolution. And the idea is simply that you try to model all the components of your spectrum. So you try to express your spectrum with a transmission spectra, you convolute with your IP profile, and you try to extract from that a radial velocity. So this is what is shown on that figure. You see the blue point, which are the observation, and you simply try to model it with the stellar synthetic spectrum. You multiply by a transmission spectra, and you make the convolution with your IP profile, and you extract from that the radial velocity. There you have the last method, and you can see that this method, I think, has really grown a lot the last years just by the number of citations that I put here on the bottom, which is template matching. And in fact, template matching, you can make different kind of template matching. So you can make template matching on the full spectrum, on the stellar line, on a single order. You can do what you want, and you always have a kind of threshold between the signal and the noise when you do the template matching. And I'm just mentioning that in the stellar activity context, I think we developed a kind of optimal signal to noise ratio to extract to correct for stellar activity. So I don't have too much time to talk about it, but it's basically a template matching to simply correct for stellar activity. Now I am here actually to talk about the line by line. The line by line, it's also a template matching method. And in fact, you see the equation, which is really simple. You simply have a master spectrum and you shift it, and you have an offset and a stretching factor to account for some distortion of your line profile. And you then apply it on a single line. As I told you, with template matching, you can apply it as well on a subpart of your line. So you have this paper about Almula et al. In 2022. And you can basically now even make template matching on subparts of your line if you want to probe differently your stellar atmosphere. So you can see that template matching has a really powerful, I would say, the resolution of the problem, in fact. However, there is a drawback, and you can see it here. If you have a spectra which is at signal-to-noise ratio of 700, if you compute what is the uncertainties on your CCF, it's 10 centimeters per second, which is what you want to detect your Earth-like planet. Now, if you look what is the uncertainties on your line-by-line radial velocity, and you see the distribution on the right, this is the cumulative distribution of the uncertainties, the median is at 5 meters per second. And this is simply because, of course, you don't have the full spectrum, so you are less precise, and it also means that you cannot detect the same effects. So what it means that if you want to detect some effect, you will need to bin your line-by-line radial velocity in some wise direction. I will come back on that later, but you need to have an idea on how to bin the lines such that effect becomes visible. There is a nice, I think, example that we encountered 1 month ago on HARPS North to probe an instrumental systematics. So we had the standard star that you see on the top, you see the radial velocity, and this star was perfectly quiet during 10 years, and during just 1 week, we have a sudden jump of 7 meters per second, which is highlighted by the red dots on that figure. Then what we did is that we observed the stars. So there was some on the log, the people they are saying that they was making some progress on the guiding software. So we looked at the guiding images, and indeed there were some issues with the guiding images. They were completely different from the past, in fact. And so at that time we say, okay, certainly it's an instrumental systematic. How we can prove it? And what Xavier did is that he simply computed the line-by-line radial velocity, and he simply binned the line on the detector. So what you see on the right, this is the physical detector, and the y-axis is the order of HARPS North, and the x-axis this is the pixel. And I highlighted the problematic date with the shadowed red region. And I don't know if you can see it by eye, but you can clearly see that you have in fact an effect from left to right. So we have a jump which is increasing from 0 meters per second up to 15 meters per second, and which is simply related to the fact that we are badly injecting the light into the fiber in HARPS North. So it's just a demonstration to show you how you can use line by line. Another nice aspect about line by line is not only for instrumental systematics, you can also think about it for the stellar activity. We know that the main difference between stellar activity and planetary signal is that we expect stellar activity to affect each line in a different way. And so it has been proved a lot. So if you look at the line depths of the line, they are changing differently. The line width, it has been showed. But on the radial velocity aspect, it has never been proved, I would say, so far. And so you have a very nice data set, if you want to check that, which is the data set of AlphaSNB 2010 with HARPS, where you see this really nice modulation on the calcium HNK line with the rotational period of the star, which is 36 days. If you look at the CCF, you have 8 meters per signal. If you look some lines, you can clearly detect a change of the activity signal. So you can go up to 50 meters per second. Then you look another line, you don't see any activity signal. And you look some other line and you see actually a negative amplitude. I will come back onto those lines later. But actually, it was for us the sign that indeed stellar activity was differently affecting the stellar lines. So what is the toy model for the moment that we have? It's that one. So on that graphic, each line, each row, it's stellar lines, and each column, it's a different component of the model. And on the left, you have the planetary signal, and you have also the stellar activity, which is slightly changing from line to line. And you have, of course, white noise components. And the first thing that you may think to do in that toy model is simply to make the difference of two stellar lines, of two radial velocity signals. If you do that, you kill the planetary signal, and in fact, you will boost the component, the contamination by stellar activity. So it's something that has been used, I think, a lot. So for instance, if you look at the color index of Zekmeister et al., it is exactly what the color index is doing. It's computing this difference between orders, in fact. And it is also what we did in my first paper. We are using the line depths. So we make different line by line radial velocity based on the depth of the lines. Another thing that you can do is that toy model, you can think, okay, I can also decide to only select lines that are unsensitive to stellar activity. I will try to convince you that it's a super bad idea to do it now, but it's still possible. When you have that toy model, this is your first, I think, reflex, let's say. So actually, there is if lines are differently sensitive to a signal, you can try to begin to play with that. And in fact, you have this paper about Lizogorsky. They are not really doing line by line, they're doing chunk by chunks. So they take several pieces of angstrom of your spectrum. And simply, they try to look what is happening if you use chunks that are contaminated by telluric and chunks that were contaminated by stellar activity, with the magnetic cycle. And what they show is that you have a sensitivity in your periodogram simply depending on the chunk that you select. And of course, if you remove the problematic chunk, you boost the signal of your planetary signal in the periodogram. In fact, we did something really similar with alpha CNB again. So you can select the lines that are unsensitive to activity or lines that are strongly sensitive. And as I mentioned before, we had this trouble of lines that were anti-correlated with the stellar activity signal. And honestly, we had no explanation for it. And if you recall the inhibition of the convective blue shift framework, you cannot have such lines. They don't exist. Typically because your bisector either simply shift to the right and you don't have more convection, or, I mean, it was not explained in the framework. So what we did is that we tried to understand why you have anti-correlated line. And so for each line in the spectrum, we had as well atomic parameter, like is it the iron line, is it the calcium line? We have the elements, we have the transition. We also know where the line is on the detector. It is on the left, on the right. We know all that, actually. We have a lot of information. And then we try to fit a machine learning algorithm to understand why there was anti-correlated line. So what we did is that we take a group of lines, anti-correlated, a group of lines strongly correlated with activity signal, and we put atomic parameters. And if you look at the atomic parameter space, which is displayed on the bottom, you don't find any splitting of the two groups. So it means that on the atomic perspective, the two groups are exactly identical. And then we simply include another set of parameters, which are simply the shape of the lines. And so is the line left blended, right blended? What is the shape? We introduce some parameter for the morphology. And here you can see that the two groups were perfectly splitting, in fact. So what is happening and what we interpreted is that when you use a template matching method, you have really dangerous bias or really dangerous degeneracies of the problem. Simply because if you have an asymmetric line profile undergoing a symmetric distortion, it's also introduced a radial velocity shift, which is not a real radial velocity shift, but which is simply a degeneracy of the problem. And that's really concerning. So, because for instance, if you go toward now M dwarf, you know that in M dwarf, most of your stellar lines are actually blended, and compared to G dwarf, and even in G dwarf, we already have problem to signal interpretation. Just a parenthesis to say that the fact that you cannot trust the signal that you see or that you cannot interpret it doesn't mean that you have to reject it, that you have to throw it away. In fact, it's the opposite. You have to keep all the signal if you want to increase if you want to decrease the photon noise. You have really to use all the stellar lines. Simply, you have to be careful when you try to interpret the signal that you are seeing in radial velocity. So we think as well that it's introduced a really concerning aspect, which is the kind of question, is insensitive line existing? And in fact, I think that no, you can make a selection of insensitive lines. The trouble is that if you try to do it, then you look your star 1 year after, and this selection of line is no more working. And I mean, it's also no sense. If a selection of lines is working, it should always work for stellar activity. And what we think is happening is that you have actually two activity effects that are canceling each other. You have the inhibition of the convective blue shift with an alpha coefficient, which is always the same sign. It's a factor between 1 and 3, if you remember what I mentioned in the introduction. And you have another effect, for instance, the Zeeman broadening of your lines with a beta coefficient. And the Zeeman broadening with this beta coefficient is changing of sign depending if your line is blended left or blended right. And we make this nice exercise. So we make two groups of lines that are symmetric, left blended and right blended, and we look how the radiosity signal were looking. And if you do it, you can see that you can mitigate the stellar activity signal by simply taking only right blended line. And for us, it was really a strong proof that it was simply an artifact. It's really a degeneracy of the problem, but it's not a real effect, in fact. Another aspect to mention is that when you do line by line, you cannot make approximation. Otherwise, you can have really strong surprise on the signal that you measure once again. And you really have to carefully select your line and the windows that you select for your template matching. And so for that, we developed a code, which is called KitKat. And it's really a simple algorithm, which is making a local minima and maxima to detect the border of your lines. So KitKat is not public, but I know that there is another public code, which is called Raccoon by Lafarga et al. 2020, which is doing something of really similar. So the idea is really to have a good selection of line such that you can trust slightly more your line by line radial density. As soon as we did it, so then when we understand that we cannot believe what the blended line were telling to us, we simply began to remove them. And what I plot here is the activity signal as a function of the line depths. And on the top, this is for anti-correlated line, and on the bottom, this is for correlated line. And the different subplot is when we began to remove lines because they were blended. And you see from left to right that first we remove completely the anti-correlated lines, which is for us a really strong proof that the signal was simply spurious. It's not a real signal. And another thing that appears for correlated one is that you see this nice shape with the line depths. And if you look carefully now, the relation, so the strength of the signal as a function of the line depths, you recover loosely the factor 3 that I mentioned in the introduction in the inhibition convective blue shift framework. So it was, I think, a convincing proof that we detected the effect. Now, I talked a lot about the line-by-line radial velocity, but in fact, you can measure other metric on your stellar lines. For instance, you can try to measure what the core of your lines is doing. So I will call that the depth by depth in analogy to the line by lines, so DBD. And for instance, here you have an example, you have a stellar lines, and you see the line by line radial velocity, which is, you don't see any stellar activity signal, whereas if you look what the depth is doing, you clearly measure the stellar activity signal of alpha and B. And in fact, you have a lot of studies that investigate that aspect. I'll put them on the bottom left on alpha and B. And what I can already tell you is that there is no relation between lines that are changing with depth and lines that are affected in radial velocity. In fact, this was my master thesis, and we didn't find any relation between the two groups of lines. Now, you see that the problem is quite becoming complex because I am talking about line by line radial velocity, depth by depth radial velocity, depth by depth matrix. How do you describe the stellar activity problem? And in fact, we tried to express it in a different way. So the idea is the following. If you have a radial velocity signal like that one, and if you have an activity proxy like the green one, which is the bisector, what people do is that they'll do the bisector, the parallelogram of it. If you do the parallelogram, you found the same peak. So clearly you can say, okay, my signal in radial velocity is not true, it's simply induced by stellar activity. And then you can make a correlation between the two signals. And if you do it, you found a pretty bad correlation in that case, whereas the parallelogram are identical. And I think that people know now what is the answer. It's simply because you have a phase lag between the two signals, which is decreasing the linear correlation and introducing what we call elliptical or circular correlation. So the idea was to say, okay, let's try to represent the problem differently. I look what is happening at a fixed period. So let's say at the rotational period of the star, I take the best fitted sinus from my parallelogram or my Fourier transform, and I will plot the power on the radial axis and the phase of the signal on the polar angle simply. And you see that it's, first you remark that the two signals are now at 90 degrees of phase, so it's a circular correlation. And it's nice because you can begin to plot all the time series that you have. So not only the radial velocity in the V-span, but you can plot all your activity proxy as well. Calcium, H alpha, really the one that you want. And I recall that actually we have 3,000 of time series because we have each line by line radial velocity. And now, if you really want to have a periodogram, you have to scan through different periods. And this is what you saw on that what you see on that animation. On the top, this is the periodogram of the CCF moments. On the left is the radial velocity. On the right is the contrast. And on the bottom, you see basically the line by line radial velocity on the left. And on the right, you see the depth by depth. And you can clearly identify that at the rotational period, if I try to make a stop here, you have a lot of different behavior on the line by line radial velocity. And for the depth by depth, you can clearly identify that almost all your lines are going in the same direction. So you can try to use that to basically diagnostic what is your signal. And if it's an exoplanet, I recall all the lines are going in the same direction. Whereas if star activity, you see that it's going a bit in all the direction. You have different phase and different amplitude. So you can try to use that to disentangle the nature of the signal. And in fact, it's quite similar to what Lizogorsky proposed in 2021. Another thing that you can do, it's that with the depth by depth, you can train a machine learning exactly for the anti-correlated line and the correlated line. You try to form a group of lines that are changing in depth a lot and a group of lines that are not changing in depth. And you're trying to understand why there is line affected by activity and why you don't have. And if you do it, basically you will find that you have really atomic parameters that are explaining this behavior. So it's similar than in the paper of Wise et al. 2022. And what is really interesting is that if you look now, what is the formula, which is predicting the change of a line with temperature. I give you here the formula, which is the delta R is the change of delta R is the change of the line depth as a function of a change of temperature in a stellar atmosphere. You can identify the excitation potential. You can identify the ionization energy. You see that you have the line depth itself and the atomic number, which is entering. So in fact, the machine learning algorithm is exactly predicting the parameter that the formula is predicting. Now I have to admit that actually the drawback is that if you really compute the formulae, you don't find exactly the sensitive lines. So it seems that there is still something to understand here. But I think that at least on the depth by depth, we begin now to understand more and more what is the star activity inducing on it. Now, as I told you, line by line radial velocity, it's a template matching method. And in fact, when you make template matching, you have some issues. Typically, when you have some systematics that your template matching method is not able to capture. This is what happened. Here you see on that example a line where you see the strong signature of 600 meters per second, which is in fact induced by a telluric line, which is crossing a stellar lines. And that's a huge problem because in the time domain, those signals can be really complex. So it depends on the depth of the telluric. It depends on how many telluric are crossing your line. What is the phase difference between the two? So here you see 4 line by line radial velocity, and you can see that in the time domain, all those signals are strongly different. So what it means that in my previous toy model, I told you that there was a planetary signal, the star activity, some white noise, but in fact, there is also another component, which is the heterogeneous noise. And that component, it's really a trouble for when you do line by line radial velocity and you want to remove it. Why? Because if now I make the difference of 2 stellar lines, perhaps I am killing the planetary signal, but I have now a proxy which is more contaminated by the heterogeneous noise. So that's why you really want to remove that component. And so the idea that we had is that, okay, instead of correcting those contamination in the time domain, we go back to the spectrum in the wavelengths domain, simply because, for instance, if you look the telluric in the wavelengths domain, this is what is shown on the bottom, they really have some predictable behavior. Basically, we know exactly where they are. We can estimate what they are doing in depth, so we can correct for them. And you see on the bottom plot, the spectrum that we obtain after the telluric correction. So how does it work to correct for them? It's actually very simple. The first thing that you need to do, again, is to compare spectra. So if you want to compare spectra, you need to remove the continuum. So you need to fit your continuum. And for that, we use a code that I developed at the beginning of my PhD, which was Racine. But the idea is that you try to be precise on the continuum normalization of 1D spectra. And in fact, we demonstrate that we had a precision down to 0.05%, which is extremely precise. As soon as you have a normalized spectrum, you can simply look your flux. And here, for instance, you have an example of a line which is contaminated. You have a suspicious behavior on the wings, which is introducing a 1 kilometer per second effect on the line by line radiosity. Now, if all your spectra are normalized, you can simply overplot all of them, and you can make any kind of sigma clipping algorithm that you want to remove the systematics. And so, in fact, this is exactly what we did. So you overplot all your spectrum. So you have the time on the y-axis. The flux is the Z color, simply. This is what we call a spectral time series representation. And if you remove a reference spectrum, you can highlight the systematics. Oops, sorry. My ordinator crashed, I think. Sorry for that. Oops. Trying to. Yes, I saw that. Thank you. Okay, it was here. Oh, sorry. Very sorry for that. Yeah. And so you basically see the anomalies, and what we develop is that post-processing code, which is called the YARA, that perhaps you already heard, which is in fact, to be honest, another template matching method, where the idea is that you try to correct in the flux domain for all the systematics, such that you clean afterwards your line-by-line radial velocity. And here you see an example. So this is on the top before YARA, and on the bottom this is after YARA correction. This is another example in the blue part of the spectrum, where you see basically the contamination by the ghost of the fiber A. You see the contamination by the ghost of fiber B, Fabry-Perot, and you also see the thorium-argon bleeding on the fiber B. Another illustration of YARA on the telluric. So you have the spectrum time series on the bottom left, and you have the equivalent representation with the animation that you see here. And you see the telluric that are drifting with time, exactly like here. And you have a stellar line here that we look. And if you look, what is the line-by-line radial velocity of this line? You see these strong systematics that I mentioned before. And we were able to decrease them by a factor of 4. This is for the telluric, but there is, of course, other effects. So you see on the middle, this is the stitching. You see as well the ghost on the bottom. So I don't have too much time to explain too much how it's working, but you can see the paper. And basically, the idea was really to remove all this heterogeneous noise that I mentioned at the beginning. Just to say that, of course, if you improve the flux at the spectrum level, you don't only improve the line-by-line radial velocity, you improve the radial velocity in general. And here you see the effect on the CCF. So you can clearly, you can extract what is the radial velocity component at the CCF level of the contamination corrected by the pipeline. And you can see that in most of cases, the peak-to-peak correction is about 10 centimeters per second, which is again something that you want to remove if you are interested by a Hertz-like planetary signal. Another way to show it, again, we take the polar periodogram. So we go this time not at the rotational period of the star, we go at 1 year. If you have a systematic, your line-by-line velocity will see a strong 1 year signal. This is what is represented on the left. And you can see after YARA processing that any line-by-line radial velocity was strongly corrected from 1 year systematics, in fact. This is an illustration of the pipeline on a single night. So you can see the improvement. We are going from 2 meters per second down to the instrumental limits, 50 centimeters per second. And this is on 10 years. I think this is more interesting. We have these cases where we corrected for 1 year systematic, and the signal that disappeared on the star was actually a planetary candidate at the 600th day by Feng et al. 2017. And what happened is that in that cases, you have another signal which is at 1000 days, which is communicating with the 1 year systematics to introduce a peak elsewhere in your periodogram. And this is really something that happened a lot with long-term signals typically. So I am finally reaching the point that I promised at the beginning, how we can improve the wavelength solution or the NZP with line-by-line radial velocity. And in fact, there is two ways to do it. I will say there is a good way, which is the one described, which is basically the fact that you try to improve your algorithm, you try to improve the wavelength solution algorithm. This is what we did for the new Espresso DRS. We try to improve the algorithm, but you have also more fancy algorithms like Excalibur by the Express team, which are also very interesting. You have another way, also in English, I'm sorry, it's called evil, but in French it's brute. And it's because it's a brute way to correct for it. And the idea is that if you want to correct for the nightly 0 points, what people tend to do sometimes is that they just average all the stars in their program. And I would like to convince you that it's a really bad idea to do it. So the idea is that one, you have a radial velocity of a star, which is a superposition, as I told you, of planetary signal, activity, and instrumental systematics. The people that choose that kind of algorithm say, okay, if I take now the average of dozen stars, the planetary signal will somewhat remove, the stellar activity will remove, and I will only, I will remain with instrumental systematics. So I can tell that is roughly the signal that I should correct for. In fact, this is completely wrong at the meter per second level. This is based on all paper of in the 90s where the instrument was stable at 10 meters per second. So when the instrument was the limitation, but today it is not the case. If you take the average of a stellar line program, I mean the average of stellar observation, you simply have the average of the planetary signal, the average of the activity, and the average of the instrumental systematics. If you remove that, you take the risk to introduce other systematic and far more complex signals. And here is an example on that star where we have completely different periodogram. For instance, on the green, it's with the rapport processing, and we don't correct for we don't improve the wavelength solution. And on the blue, this is with this method of night 0 point correction. And we think that it's a really bad idea to do it in that way. I will try to argue more why it's a bad idea. The idea is that if you average star, you don't solve for instrumental systematics. At the detector level, what you have, it's always a superposition of several components. This is what is represented on that figure. So you have the detector, wavelength versus pixel. And you have, for instance, two components. So you see that on the time domain, it's two random time domain vector. But the idea is that they are distributed differently on the detector. When I have a spectrum and when I have a spectrum, sorry, the stellar lines, what they are doing is that they are probing my detector by the stellar lines. And the more deep is the line, more strong is the weight, or more high is the weight. If now I take another star, let's say a star number 2, the problem is that the two stars don't have the same systemic radial velocity. So I probe the detector differently. Also, my second star has not the same effective temperature. So in fact, the weights of the line are changing, even the line themselves are changing, such that at the end, I cannot tell that in the time domain, the effect is the same. What is true is that at the detector level, I have the same effect, but in the time domain, it is absolutely wrong. They are not the same effect. However, I understand why people tend to think that instrumental systematic are affecting all the stars, and I will try to show you that we can use that, but not in as previously. We can use that in a different way. This is the way that we developed. This is in preparation. And the idea is that we use the line-by-line radial velocity with the PCA. So when you take your radial velocity space, so you have an n-dimensional space. Each dot, it's a line-by-line radial velocity time series. As I told you in the toy model, the planetary signal is affecting all your lines. So it means that the planetary signal is the barycenter of the cloud. Now, if you know a bit how PCA are working, PCA are insensitive to barycenter. In fact, they are looking for the elongation of the axis. It means that if you perform a PCA on line-by-line radial velocity, you will never detect planet, but only the contamination. And if you can detect the contamination, you can try to correct for them. So this is what we did. And this is the result of a PCA on line-by-line radial velocity. And so what I presented here is on the top, the time series, on the middle is the periodogram, and on the bottom, this is the strength coefficient fit on each line-by-line radial velocity and simply plotted in the detector space. And what appeared from the PCA was first a signal that we were expecting on HARPS, which is the thorium aging of the lamp. So you clearly see this drift. And when we change the thorium lamp, we suddenly have a jump. So we detect it. We see some systematic that we don't know about, but that are smooth on the detector. So clearly it is an instrumental systematics. And we also detected some excess power at 1 year. Now I did that for 1 star, but I can do exactly the same for all the stars of my program now. And if you do so, you can see that suddenly you found somewhat the same component. And this is how you can then use the fact that all the stars are affected in the same way. You can try to group the components together, like here, here as well on this second component. And you can try to fit, you can try simply to map the contamination on the detector. And so this is what you see on that image. So this is the 2 components that we fit on HARPS, for instance. On the top, this is the thorium aging. So it's based on 10 standard stars that we observe, and we can then fit a model in 2D on the detector of HARPS. And then you can use those maps that are now really the effect on your detector to extract the time series signal. And this is what you see on the right. On the right, you have the time series vector that are extracted. And you can use those vectors then to decorrelate your radial velocity. And here it's simply a comparison of the 3 versions or the 3 improvements. So on the top, you have the DRS, which are the nominal radial velocity. On the middle, this is when you correct at the flux level. So this is what I call EPRV1. And now you have EPRV2, where we remove those components in the time domain. And so here, just to prove you that first, we don't absorb planetary signals. So you see that the planets that are on the left are still here. This is the example that I presented to you in the introduction. So this superhertz in the habitable zone, you see that you strongly decrease the signal. So likely it was not a planet, but really it was simply the instrument that was aging with time. And here you have as well a tau ceti. And you can see as well on tau ceti that the 1 year power that was still remaining after EPRV1 is now really strongly removed after EPRV2. So I will conclude. So I hope that I convince you that the line-by-line radial velocity are really powerful. First, if you want to make data exploration, it's really a super nice, convenient tool when you want to understand you have a systematic. Let's say that you are, sometimes you see a strange behavior, you do line-by-line radial velocity, and you can try to trace back where this signal is coming from. So it's really a powerful tool, diagnostic tool, in fact. You can also use that simply because in the toy model, stellar active, the planet is affecting all your lines. Whereas if you have systematics, you will have different behaviors. So you can use that to assess the planetary nature of a signal. You have some drawback. The fact that if you make template matching on a small wavelength range, you are strongly sensitive to local systematics, and you want to remove them if you want to interpret the signal afterwards. And because you have a kind of lower precision, of course, on the single lines, you usually need to bin the stellar lines in some direction. So you need to have an idea, okay, I want to investigate what is happening on all the stellar lines that are deeper than 0.5, or I need to investigate what is happening on excitation potential line with higher than 6 electron volt or such kind of things. You need to have an idea of the binning that you want to perform. And I think which is really for me the most important is that with line-by-line RVC, we can begin to open a better understanding what is happening at the physical level of the stellar lines. And for stellar activities, this is really important. So I show you that for the depth by depth, there is really good hope that we can have a model, physical model soon. And for the line-by-line radiosity, we don't have yet a full explanation, but we have these dependencies, for instance, on the line depths of the signal. And I think I will end here. So if you have any question, please don't hesitate.
Well, thank you for an excellent talk and a very impressive set of work that you've done. I would definitely give you a PhD if you gave this talk in a thesis defense. I feel like you're in good shape.
Thank you.
Lots of clapping emojis in the participants list. Let's open the floor up for questions. So if you have a question for Michaël, raise your hand if you would, and I'll call on you. Okay. Nathan Hara, I see your hand up. Go right ahead.
Yeah, thanks. Very nice talk. Can you re-explain what are the plots, the blue and red plots in the detector space? I'm not sure I understood.
That one?
Yep.
That one, you mean? Okay.
Yeah, these
So,
ones.
Yeah. So here you have the here you have the time series. And in fact, if you fit that time series on the line-by-line RVs, you get a strength coefficient, right? And what is plotted here is simply the strength coefficient normalized by the standard deviation of all the coefficients. So that's why I call it the Z-score, in fact. Is it more clear or not? So basically, if it's red, you will have the same signal than this one. If it's blue, the signal will be reversed, for instance.
Ah, okay, okay.
It's the strength coefficient of the multilinear fit.
Okay, thanks.
Okay, other questions in the audience list? Dave Latham, I see your hand. Go ahead.
Fantastic stuff, Michaël. Let me make sure I understand the big picture. You made the planet around Alpha Cen B go away because of thorium argon lamp aging?
This is not Alpha Cen B. It's another star. I don't remember which one is it. It's another one.
Okay, so what is the status of Alpha Cen B? Have you looked at that?
We look about Alpha Cen B, and indeed we found some signal that we need to understand. So it's not clear yet if it's planet or not, but yeah, there is indeed some signal.
Okay, I'm glad I asked that one. Now for Tau Ceti, where do we stand with Tau Ceti? There is a planet, there isn't a planet.
So there is, I think, there is different paper of people that publish planet around it. On our side, we also found signal, but that are not the same that the one published. Typically, for instance, we don't found the 600, we found another one at 1000. And I think for the other one, we are quite in the same way, the same direction for the other signal. Yeah. But yeah, there is, for us, there is also planet around the Tau Ceti.
And that's based on what, 2000 observations? How many observations?
I think, no, not 2000. I mean, we have 400 nights, something like this.
Oh, it's only a few hundred.
Yeah, only a few hundred, perhaps 300 observations, I think it's 300 nights, something like this.
But you definitely made the 1 year alias go away.
Yeah, that's the important point.
Yeah. Oh, fantastic.
Like that Dave's just naming names of stars and asking for details carefully. None of these stars are labeled in these figures. Okay, Sam Halverson, I see your hand. Go ahead.
Yeah, thanks for a wonderful talk. A couple of questions. So one is sort of a processing or a philosophical question. So in the line-by-line least squares fitting, you're basically assuming two free parameters, right? One being velocity and the second being kind of a residual like amplitude offset for the entire chunk, right? Do you think there's ever going to be a point, especially with the tools you develop, where effectively the amplitude is no longer a variable, if that makes sense? And in which case you're not actually fitting for an offset, right? You're only fitting for velocity, in which case it's not really a fit. You're just sort of computing the velocity offset, assuming all of the intensity variability you're seeing between your template and your flattened template and your flattened spectrum is only velocity. And that gives you things like pixel by pixel velocities. But is it ever going to be that good, or do you always have to fit for an offset?
So I think that you always have to fit for, so I don't know if we should ask that to Xavier. I think we have to fit for the offset, because otherwise, if you have some issue, in particular with the continuum or something like this, you really get strong signature in radial velocity, about 100 meters per second. So we need it for sure. That's why we include it.
Yeah, I guess it's a question of, because your continuum normalization is so repeatable now, is it necessary? I suspect the answer is still yes, just because the slopes are really steep. And so even a small intensity offset is going to, screw up your RVs, but I thought I'd ask.
But first is if the normalization is good, even if you include the offset should be around 0. So I don't know if it's changing a lot or not. It's true that we didn't check that we need that offset anymore in the model. That's a good question. Perhaps we could check on the side.
I only ask because if you don't need it, right, there's no more, you don't need 3 pixels to get your 2 free parameters, right? And so you can get every single pixel now as a velocity, which you're kind of inherently doing in other ways. But anyway, the second question I had was, you mentioned something on alpha sen B with the depth variability. You said something where you don't see any correlation between the individual line RVs and the depths for any lines, or just the active lines, or could you revisit that?
Yes, where is it? So it was in my thesis. So what we did is that we test is that we look what are the line with strong depth variation, and we try to see if it was the same line with the line by line radial velocity variation. And what we show is that exactly in that case, there is just no correlation between the two. So if you try to select lines that are not showing depth variation, actually we are the worst line by line radial velocity afterwards, simply because we were rejecting lines and the noise was increasing. So I think there is a complete decorrelation between the two, which is also making sense because this is not the same physical process. Depth by depth, as far as we understand, this is really related to a change of the temperature in your stellar atmosphere. Whereas line by line radial velocity, it's really the inhibition of the convective blue shift. And I don't see any reason why there should be a strong correlation between the two effects, in fact.
That's quite interesting. So we actually put out a paper where we do have a population of lines where, for alpha sen specifically on HARPS data, where the depths correlate relatively strongly with the individual line RVs. So I'd be curious to compare on that. We also only focus on a couple of rotation periods where the sampling is almost uniform throughout the entire rotation period, but I'd be interested in following up on that. Thanks.
Okay, that's interesting.
Okay. Other questions from the audience? Oh, there you go. Ansi, Hannah?
Yeah, thank you. Hi, Michaël. It was an excellent talk. Thank you so much. I have a question from one of the slides that you presented here. Maybe I just missed something. That I remember that slide 67.
67.
Okay, I was just trying to distinguish between the periodograms here with ERR V1 and V2. So I'm not sure whether I'm missing something because I was trying to distinguish.
Actually, yeah, there is actually no difference, and that was the point because I wanted to highlight that the planets were still there. In fact, the planet that you see here, they were not removed. But on that target, you don't see the long-term systematics.
Okay. So what difference does it make from ERR version 1 to ERR version 2?
What improvements you mean, or what is the difference?
Yes, yeah. What's the difference? Like what makes it different from V1 to V2?
So it's really
not exactly from this. Yeah.
Yeah. So it's really what I described. ERR V1, you are really simply correcting at the flux level. So you correct everything that you can at the flux level, and then you reach a new frontier, which is simply the flux, the photon noise at the flux level. So you don't see anything significant. And then you have to go in the time domain simply to correct. So you have to try to extract new proxy to correct for your systematics. And this is where ERR V2 is beginning. So as the frontier between the flux domain and the time domain is the frontier between ERR V1 and V2.
Okay, that's great. Thank you so much.
I don't know if it's more clear like this.
Yeah.
Okay, we are at the top of the hour, and I don't want to keep folks over. So if you have lingering questions for Michaël, I suggest you email him after the fact. Thank you again for an absolutely wonderful presentation. This was a joy to watch. And so I invite folks to do the little clapping hands emojis if you want to show your appreciation. Or James just going for it in the video. I like it. So yeah, thank you again to Michaël. Thank you to everyone for calling in.